Um, I was really happy with the exams. Thank you. Hopefully you are equally happy. If not, come talk to me. I'd be glad to discuss the exams with you. I want to look at integrals a little bit differently. When we think of this integral, we used to write this as an area, right? What was it the area of? This requires response to what's on the screen, not to what's on the paper of writing. What is this the area of? Between our points A and B, right? So I have some graph. And it's this area. I can also think of this as going along the x-axis. Okay. I want to stretch this definition. I want to think about integrating a function of more variables. But instead of thinking about an area, I want to think about this along a path. So instead of writing the integral from A to B, I'm going to write the integral and then I'm going to write it over C. So there's just a subscript C on here. And that means along some curve. So this time, here's C. Now I'm deliberately drawing something. I don't know what the equation is. Doesn't really matter off the top of my head. But I've got this curve, starts at this point down here and goes to that point up there. So origin, terminal, sorry, initial and terminal point. And that's x of t, y of t, and it increases as I go in that direction. Let's assume that our function f is defined on an area that completely contains this curve. So whatever the domain is for this function, all of the points of this curve are inside the domain. I don't have to worry about being undefined anywhere. The function f is defined on some region that encloses this curve. Now, normally we would ask, what's the volume under the surface for f of x, y, right? I don't want to do that. I want to try and do this picture. Wait a minute. F of x, y has a value at every point along this curve, right? So I could think of a z value above all the spots on that curve. A fence. I want you to imagine a fence whose height is given by our function f of xy, and the fence is on that curve. So we make the little pickets, the wooden pieces, the slats that make up our fence, and we draw the fence along this path. Now I can ask the same question. What's the area of my fence? Now, there's a nice picture of this on page 1076. So let me throw that picture up here. There's my curve in the XY plane, right? But instead of just taking that in the XY plane, I'm looking at the Z values. That's f of XY. And I can ask you, what's the area of this? How much wood do I need to build this fence? I need to integrate. I need to add up all the little slats and make them smaller. Same bullshit we did before, right? But I'm measuring along this curve, not along the x-axis. The x-axis is straight. That's not. So if I want to integrate this, I need to think about something I actually didn't put up there with the integral. What's missing up there? Integral of f of x and y over the curve. What's missing? A differential. If I was going in the x direction, then I'd use dx. If I was going in the y direction, I'd use dy. What the fuck? What direction am I going here? I'm going along my curve. If I'm going along my curve, I can cheat and say what I really want to use for a differential is a differential that measures that curve. Arc length. The right way to do this integral is not dx, it's not dy, it's ds. Wait a minute, wait just a freaking minute. We had a formula for ds, especially when I'm dealing with a parametric curve. My curve here is defined x of t, y of t. I got to go all the way back to arc length. Find me arc length. You can find it in several different places. You can find it in chapter 13. You can find it in chapter 8. We did this semester. We did this last semester. I've seen this before. Yeah. What's ds? That's what I'm doing a curve in 3 dimensions. This curve is only in 2 dimensions, so I don't need a z of t. But that is my arc length differential. which means I can do this entire integral in parametric form, provided I know how to make a parametric version of my curve. Now, I'm kind of irked at myself because I physically 3D printed one of these things on a 3D printer. And I forgot it in my office, so I will bring it on Wednesday to show you what this looks like. But I'm going to do the following problem. I want to do this integral. The integral of x, y, ds over the curve C, where C is the part of the unit circle in the first quadrant, oriented counterclockwise. Why do I need an orientation on an integral like this? I'm going to walk along the fence. I'm going to measure the height of the fence, right? I need to know which way I'm walking. So the oriented counterclockwise means I'm going this way along the circle, not this way along the circle. So I need to know when I draw this curve, that I'm going that way. Now, please note the important part. ds up there at the top of the screen got turned into stuff in terms of t. If I want to do this integral, I need to turn everything in this integral into t. That means I need to know parametric equations for this curve. I'm back to chapter 13, describing curves in 3 dimensions. Back to chapter 10, parametric and polar descriptions. So my question to you, how do I draw this part of this curve in terms of a parametric equation? That'd be the ugliest part of this process every time, figuring out what my parametric equations are. But I can cheat and use any parameter I want. And this is part of a circle. So what's a good parameter to use for part of a circle? You had to do it on the exam. When you think in circles, what coordinates do you want to think in? Which means I should use r and theta, right? I'm on the unit circle. What's r? And theta will then tell me where I start and where I end, won't it? Oh, there's my parametric set of equations. X is r cosine theta. I'll use t instead of theta. Oh, it's the end of the world. You changed the letters on me. How dare you? Big deal. 1 sine t. And 1 cos. Notice that also tells me where I want to start and where I want to end in terms of t. What's the smallest value of t I'm using? And the biggest one? There you go. Notice what we can now do is turn everything into parametric equations and make this an integral in t. And if it's an integral in t, then I can do it like a regular integral. Hang on a second. This integral becomes the integral of x times y, cosine t times sine t, ds. What's the derivative of cosine? But that's squared, dx dt squared, then derivative of sine, but that's squared, and then that's an integral dt. Hey, wait a minute, if that's an integral dt, its boundaries should be in t. Son of a, I just turned this entire problem into a regular integral. A line integral, the ds part takes the curve and straightens it out so I can do an integral in t. I've unwound my curve with this. First question, what's under the square root? Sine squared plus cosine squared, that's a 1. Which makes this the integral from 0 to pi over 2 of cosine t sine t dt, which happens to be a really easy integral. What do I do? U equals sine, du equals cosine. Or u equals cosine, du equals minus sine. Your choice, doesn't matter. I'm going to do u equals sine. Du is cosine t dt. And this becomes the integral of u du. Sine of 0 is 0. Cosine of, sine of pi over 2 is 1. That just became a really easy integral. The area under this curve is 1/2. But this area is not measured flat. It's measured around the circle. I am about to do a crappy artist's job of drawing this picture, but I promise to physically bring you the 3D printed version on Wednesday. This is the graph of x times y. Here, it's 0 because y is 0. Here, it's 0 because x is 0. But as you go around, x is going to get bigger, y is going to get bigger, right? And then x is going to start getting smaller. Oh, this is going to go up and then come down. What I have is a fence that's low, up, low. But it's wrapping around a quarter circle as opposed to being straight. And what this integral did was it unbent that fence so I could look at it straight on and do an integral. This works all the time. The path integral or line integral of a function along a curve. Instead of writing the integral of f of x, y ds over the curve C, I'm going to write f of x of t, y of t. And then I'm going to put in my arc length piece here. And I'm going to integrate from A to B, where A is the starting point of my curve, and B is the ending point of my curve. Question. As long as I can write the parametric equations, I know how to do this. So instead of me doing an entire integral problem, let me start with this question. Here's a curve. What are the parametric equations that describe this curve? There are several different ways to do this. There's one I think is most direct that we learned back in chapter 8. Here's my curve. How can I describe this parametric? The advantage in this case is that I've already written it as a function, right? Y equals x squared. So if I just change the variable to let x be t, if x is t, then what's y? Which means those are my parametric equations between 0 and 1. We did parametrizations back in chapter 13, where we wrote our equation as r of t. That was what x of t and y of t was, right? Remember, r of t was exactly this description. By the way, that makes ds the length of r prime of t dt. And that's what we did back in chapter 13. That's even the way we wrote it. I like thinking of this in vectors. I think that's helpful. But it will also be easy to think in parametric terms. Questions? If my curve is made up of different pieces that are glued together, here's a curve made up of 3 individual pieces of line segments. Now, this would piss off a lot of people because I said this is a curve and it's got corners. Didn't we just talk about this in history on Thursday? Well, what I really want to do is, instead of thinking of this as one curve, I want to think of this curve as the union of 3 individual pieces. The window, the air pressure from the window being open back there. See, breeze. Yeah, Sister Brennan haunts over in St. Joe's, not over in Mara. The elevator is dedicated to Sister Brennan. If you don't thank Sister Brennan when you get on the elevator, the door won't shut properly. It's happened to me for 15 years. Okay, so here's my question for you. We did this back in chapter 13. How do we describe the line segment C1? We did this. We figured out the parametric description of a line segment quite some time ago, but we did do it. Oh, that's really cool. You can go back to chapter 13, look up the line segments. I need some of you to look at your index cards again, because I know it's on some of your index cards. This formula appeared both in chapter 8 and back in chapter 12 when we did lines and planes in 3-dimensional space. This is also on page 1079. So, curve one, the horizontal line across the bottom here. Oh, I forgot to write this down. 0 less than or equal to t less than or equal to 1. Every time, when we do a line segment, every time it goes from 0 to 1. So curve one here is 1 minus t times our starting point, 0, -1, plus t times our ending point, -1, -1. And then I just multiply through the vectors. And I get minus t, because I get 0 from this part, and I get the minus t here. And then I get t minus 1 minus t. Now that makes sense because the y value is always -1, isn't it? On that part of the curve. That's a horizontal line. Here, the y value is always equal to -1. That should stay constant. But now I have x of t and y of t. Or if you'd rather, what I have here is r of t. And then I can do curve 2. And then I can do curve 3 the same way. And then if I want to integrate over this whole thing, I first integrate along curve 1, then I integrate along curve 2, then I integrate along curve 3. And since I'm doing the union, I add those together. So the integral along the whole curve will be the sum of the integral along the pieces. Now, for this curve to be acceptable, those pieces must not overlap except at the very end points, and they must be differentiable. I must have dx and dy to do my ds part. So these have to be smooth curves. Wait a minute, smooth, like our vectors, smooth. C1, like our integrals in our C1, they have to have continuous first partial derivatives. Derivative with respect to x and with respect to y, same idea here. Where the hell am I going to use this? Well, there's an interesting version of our center of mass problem. If I took a wire, like a solenoid, that's a coil of wire, but maybe it's heavier on one end than the other, I could ask what its mass balancing point was. But if that mass is in a straight line, that's fine. Then we do center of mass just like we did back in Calc 1. But if I bend it into part of a circle, then finding the center of mass becomes a line integral instead of a straight integral. Page 1078, figure 6. Here's a wire that is heavier on the closer we get to the x-axis. So the ends here are heavier than the piece up here. Okay, where does it balance? Well, I would assume by symmetry, left and right, it's going to balance in the middle. But top to bottom is going to be a little harder to figure out because the closer we get to the x-axis, the heavier it gets. I'm going to have to do that integral. And lo and behold, 1 over the mass, integral of y times the density. It's the same damn formula, but we're doing a line integral instead of an xy integral. Questions? I find that to actually be one of the least common uses of this, but my personal favorite place to use this is to break up my integral ds. Sometimes I don't care about how much of the fence is bent and curvy. I only care how much of it goes in the X direction or how much of it goes in the Y direction. In which case, I'm going to rewrite my integral. And I'm going to think of the integral along C of f of xy dx, not ds, dx. Or I'm going to think of it dy. But let me just work for dx for a moment. Well, I'm going to do the same parametric equations. I'm going to put in x of t and I'm going to put in y of t. And so I'm going to get the integral from a to b of f of x of t, y of t. But now I don't get ds. I get dx. Wait a minute. Chain rule. What's dx here? Oh, dx dt would be x prime, right? And I'd square it and take the square root. That doesn't change anything. It's still x prime. So I'm going to get x prime of t dt. Not the square root anymore. That's only the ds part. And if I do the integral of f of xy dy, the only thing that changes here is what? Y prime of t dt. Give the lady a cigar, she wins. So where would I be doing something like this? If I have a function that goes in the x direction and the y direction differently, f of xy, right? Then I could think about the part that goes in the x direction and the part that goes in the y direction. So there are occasions where we will do this together, and we will think about a function and ask, what's the x part doing and what's the y part doing? Oop. Now, before you freak out on me and go, wait a minute, that's disgusting. I don't like it. What are you doing to me, Dr. Sassmore? I need to go back, chapter 12 and chapter 13, and think for a moment about work. So now I have a question for you. It may or may not be on your first or second exam sheet's formula card, but it's back in chapter 12 and 13 somewhere. What's the definition of work in vector terms? Of force and distance, right? But now force is changing over time, and distance is now measured on my curve, right? So I'll need to measure my distance along the curve. That means I got to use a tangent vector. And if I'm going to take the distance part and do it in the integral, I'll need a unit tangent vector. So I'm going to do work by doing force dot the unit tangent vector. But I'm going to do this along my curve in terms of the arc. You're exactly right, force times distance. But to figure out distance, I got to go along my curve. Wait a minute. T. What's the formula for capital T? That one I know is on your index cards, people. Wait a second, what's ds? We wrote this down not more than 15 minutes ago. What's ds? So there was a nice way to write it. Length of.
Yeah, the length of the R of R derivative of T. dt.
Those are being multiplied. What happens? They cancel out because they're lengths, they're numbers. That makes this integral, the integral over C, f dot r prime of t dt. That's, wait a minute, this is parametric. That's not C anymore. What does it become instead of C? If this is dt, that becomes A and B, where C is R of t, A less than or equal to T less than or equal to B. A dot product, right? A dot product. What's F? F is a vector. It's a force. You know, like the vector fields we were doing on Thursday. If you have a curve going through a vector field, you can measure how much work is done as that vector field pushes stuff along. Along what? Along this funky path R of t. This is the work done by a field. This is your electric field doing work, your magnetic field doing work, your gravitational field doing work. This is exactly the physics definition of work. But it's a vector field. Ready for the sneaky part? My vector field is going to have functions. Yes? PQ. What's R prime of t? Because I need to do a dot product. R prime of t is, well, that's going to be x prime of t, y prime of t. Yes? So when I do the dot product, what do I get? I get p times x prime. And then I get q times y prime. And I'm doing this integral dt. Right? So there's my integral for work. That's work. Wait a minute. X prime of t dt. X prime of t dt. X prime of t dt. Y prime of t dt. Y prime of t dt. Hang on a second. Wait a minute. The integral of f dot r prime of t is the integral p dx plus q dy when thought of as a line integral. Work is exactly the line integral we want. We're going to write this piece as dr. And so I'm going to write this as the line integral f dot dr to do work. Son of a randy-legged bandersnatch. This is exactly the same integral that we were trying to figure out what it would mean on Thursday. How do I figure out how a vector field affects things as I walk through it? This is. Once I know what a line integral is, this is the exact correct definition to figure out the work done by that vector field as I move through it. The only thing I need to take into account are things like mass and charge. So I know how we interact with the fields. Questions? The only stupid question is, do I need to keep breathing if you ask it? The answer is no.
Like, so we get a problem for work, which?
That's going to depend on how we were given the equations, right? And I think if we're given a set of parametric equations, this version is going to be really easy to do. But in order to do this integral, I'm going to have to convert it to a t integral. That's this integral, which then becomes this one. So almost all the time, the integral goes back to being this integral. Almost all the time. Ready for the almost part? Here, on page 1079, they do two different integrals. They do a line integral that starts at -5, 3, goes to 0, 2 along a straight line. And they do the integral of y squared dx plus x dy. That's work, isn't it? P dx, q dy. That's work. We do it this way, and we get a number. Then they do it along this parabola, and they get another number. And here's the interesting part. Those two numbers are different, substantially different. So here's the $64,000 question. When will the path I take matter? Sometimes, as is clear by this example, going along the straight line gave me a value of -5, 6. Going along the parabola gave me a value of 40 and 5/6. That's a huge difference. So here's a problem. I did this integral one way, I got a nice small number. I did this integral another way, I got a huge number. What about the vector field in this problem makes it go haywire? And that is really going to help me figure out which integral I want to use. Because if it turns out that which path I take is irrelevant, I'll take the nice short straight path. But if the path matters, then I want to take as simple of a path as possible. And so I need to know where the weird spots are in that vector field and whether or not that vector field is nice. That is the primary piece that is the discussion of the next section. But before I throw you all out for the next day, I want to remark that everything we've done in P and Q and dx dy works just as well in 3D dx dy dz with PQR. So all of these can be done not just for curves that are flat, but for curves that are moving in space, like my twisted cubic or my helix. A helix, you know, like an electrically charged particle moving through a magnetic field, physics 2 people. All of those lovely pieces that make up your mass spec and your instruments work because of this. This was developed for the sole intent of understanding physics. Figuring out how heat and magnetic behavior worked well. The basis of thermo, the basis of quantum, the basis of physics 2 and E&M is written in calculus because these work well. Provided I can figure out how the vector fields work. And we'll discuss that not on Wednesday, because on Wednesday we have today. Now, I would like to note to all of you, question and answer day is Wednesday. Thursday, Friday, Monday. Wednesday. You get a full week between these two things. Problem. 16-1 and 16-2 are due the Wednesday you get back. So if you ask me all these questions and then put your notes away for the entire weekend of Easter, you will forget all of it. So either do the homework before you go home or do it over break. I will see you all on Wednesday. Have a wonderful rest of your day. I didn't mean to slap you with a fish.